Hello, hello. I just wanted to introduce you to a couple of ideas with complex numbers. All right. Now, some of this stuff will just kind of be general stuff, and then I'll go through a couple of examples as well. All right. The first thing that I want to go through is just the idea of a complex number and its conjugate, and I'm going to talk about why that's so important. Now, with a complex number, you always have two pieces, one which is the real component, that's this A, and one which is the imaginary component, which is this B. Now, one of the things that you need to know about complex numbers is that they always have a conjugate. Now, the conjugate we represent by doing the Z and then a star, and it is simply A minus BI. Now, I would like to show you why the conjugate is so important, why we even care about it. Okay, so what we're going to do is we're going to take Z and multiply it by Z star, and I want you to watch what happens here. So we have A plus BI, and then we have A minus BI. And so when we do that, if we FOIL it all out, we've got A times A, which is A squared. We've got A times negative BI, which is minus ABI. We've got BI times A, which is plus ABI. And then we've got BI times negative BI, which would be negative B squared I squared. Now we know that I equals the square root of negative 1, which just means that I squared equals the square of that, which is negative 1. So we can go through and simplify this by canceling out the negative ABI and the plus ABI. So we're left now with A squared, and then the I squared turns into negative 1. Negative 1 times negative B squared would be plus B squared. You'll notice then that when I multiply a complex number by its conjugate, the imaginary part goes away. Ain't that nice? Yeah, that's nice. So one thing that this shows us is that if we have a polynomial and an imaginary number is one of the roots, if some complex number is one of the roots, then its conjugate also has to be one of the roots. If it wasn't, then there would be imaginary numbers in our polynomial. But since there are not imaginary numbers in our polynomial, then it means that somewhere along the way, that root has been multiplied by its conjugate, meaning that both of those, therefore, would have to be roots. Okay? Now, another thing that I wanted to kind of look at a little bit is how we can get a polynomial from this. Okay? So in order to do that, I want us to assume for a minute that A plus BI is a root of a quadratic, or any other polynomial for that matter, but let's just say for a minute that A plus BI is a root. Now, if that's the case, from what we just talked about, A minus BI must also be a root. Okay, so if that's the case, if we're looking for the quadratic that has these two roots, then we just need to go y equals, and then we say, okay, that means x minus A plus BI, and that would then need to be multiplied by x minus A minus BI. All right, and then from there, we can distribute the minus. So I'll have x minus A minus BI, and then x minus A plus BI. Now, you could FOIL this whole thing out, but it'll be much easier because I've got an x minus A here at the beginning of both of those, if we treat that as one unit there. Okay, so we're going to go x minus A times x minus A, which is just x minus A squared. X minus A times plus BI, so plus BI x minus A. And then negative BI times that, so minus BI times x minus A. And then, of course, negative BI times plus BI, which will give us negative B squared I squared. And you'll notice when we do this, we end up getting to cancel out these because they're the same. One's positive, one's negative. And so, therefore, if I square this, I'll have x squared minus 2ax minus, now, of course, b squared I squared is negative 1, so that means that's going to turn into a plus b squared at the end. And so I also had the minus a times minus a, which gives me a plus a squared. And so then that means that the quadratic can have this function. Now, this should kind of make sense because then we've got this kind of deals with the idea of the sum of the roots and the product of the roots as well. And you can prove this function in that way as well. But therefore, we can say that with a complex root with a and b, we can now find what b right here, what this number should be, and also what this number should be, because we know what the real and imaginary parts are. That we'll be using a little bit later. Note that, of course, there could be some coefficient out in front that would keep these same roots. Putting a number in front will not change the roots themselves. It'll just stretch or compress the rest of the graph. Okay, so keep that in mind. That will be helpful as we work some other problems. All right? Now, the last little idea that I want to go over here is the idea of what makes two complex numbers equal. And this is actually fairly straightforward. If you have complex number a plus bi, and you have complex number c plus di, these two are only equal if the real part is equal and the imaginary part is equal. If those are different, then there's no way that these two can be the same. The imaginary parts have to be congruent, they have to be equal, and the real parts also do. Okay, and so when you're looking at two complex numbers, just simplify it down to where you have just the single real part and the single imaginary part, and if they're the same, then you know that those two are equal. All right? So I hope that that was kind of a good basic idea of complex numbers. These skills are things that you will use as you go forward through the next couple of homework assignments. All right, so good luck with that. Please watch the next video with some examples.